solution, essentially. Tonight is Introduction to MapReduce. We haven't had a meetup, not counting the Hadoop one, that was just a little short while back, in quite some time. Mostly for lack of coordination and leadership. We had an idea to start a beginner's track that was committed to meeting at some frequency, perhaps monthly, even if we don't have a topic ready at hand, because if you put a bunch of beginners in the room, someone will just ask questions immediately. So that's kind of the idea. It's very loose. This is a call for beginners to participate, for anyone who's willing to speak or present, anyone who has a space, anyone who's willing to help coordinate. Because oftentimes we have all the dots, we'll have a space, we'll have a speaker, we'll have a vendor willing to pay for stuff. It's just a lot of coordination. I'm horrible at it, and so are the other organizers. So if anyone wants to just help out with that, you can get your name on the meetup, and it probably looks good on a resume or something like that. And you get to meet a whole bunch of people. That's included. Okay, I think that's it. We're hiring too at Pulse Point, so you can speak to me. I think I have business cards, so I go for them. But if you reach out if you're interested in anything that we hear tonight, or want to know more about what we do. Let's get started. So, introduction to MapReduce. The first question, this is the Hadoop Meetup. And actually, one of the challenges of being a Hadoop Meetup is that it's really hard to come up with topics because Hadoop is so broad, so many people use it very, very differently. The tools are different depending on what you do with it. So it's hard to find something that all of our members really appreciate from the same perspective, the same degree. And part of that's because, Hadoop is different depending on who you ask, right? So for tonight, we're going to say that Hadoop, the core platform of Hadoop consists of HDFS and MapReduce. HDFS is the file system, scalable, distributed file system that we're not going to get into. But it's its own project, and we can totally get into it over the course of several evenings. And MapReduce, which is what we are going to talk about tonight. There are also many, many other related projects that make up the Hadoop ecosystem, which I would propose that we actually have our next meetup, so with the interest. To going over. We could actually list out different projects, the Apache projects or other projects, and have different people present that actually use it and know more about it. I think that would be a really, really useful thing for me and a bunch of people I know, but I'd love to hear about that after we talk tonight. So let's go back to MapReduce. So there are a couple of blurbs that are pulled out of the Wikipedia page for MapReduce. So MapReduce is a programming model for distributed computing. And distributed computing is kind of hard, like concurrency is basically hard. So MapReduce provides a framework that helps you design a solution to usually a big data problem that would otherwise just be kind of hard, right? And it does that by providing two interfaces, a map and reduce, that you as the developer, as the user, are required to implement, and everything else is kind of magic. And we'll get into more detail in a bit. But that's MapReduce. So let's talk about mappers and reducers. Right? So mappers operate on each record. Perhaps we're skipping a little bit. So let's jump right down to an example. Something you could use MapReduce for is you have a whole bunch of web server logs. Web server logs actually tend to be one of the lowest denominators, because most people have seen one. So web service logs have IP address, they have the requested object, they have the user agent. So it's not hard to imagine that a web server somewhere prints out a log and is able to show the different browsers that hit different parts of the web page. And browser market share is a metric that everyone's pretty much trying to do, so that's what I said in this slide. And what a mapper would do is if you have all these logs and you want to run some analysis on it, you want to run it for MapReduce. The mapper would look at each record, look at each line in your log file, and perform some filtering and transformation. So if we're looking at browsers, the filtering would be, doesn't care about most of the logs. Probably going to parse that whole record, look for the field that corresponds to the user agent, try to pick out the browser part. And the transformation is probably just the stripping of all the extra corrupt in the user agent field. And ultimately just spit out something meaningful. In this case, it would just be the name of the browser, Firefox, Chrome, Safari, whatever. and the value. If we were doing something like just counting the numbers of time Firefox hit this web server versus IE versus Chrome, a mapper would just, for each record, print out Chrome 1, Firefox 1, and keep going. It would basically iterate a counter of 1 each time it's solid for each record. Right? This is the intermediate data, which I think I mentioned. Yeah, intermediate data, and this is part of that MapReduce bit where MapReduce provides you that framework. It also provides you with a thought process. To my mind's eye, you look at the problem, and I think, how do I look at browser market share? And ultimately, if you want to think about what your final result set looks like, but your second step is to think about what does your intermediate data set look like. So ultimately, you just want Firefox 2 million hits, Chrome 1 million hits, basically just a sum of these individual hits. Your intermediate data is basically just a count of 1 hit counter for whatever browser that corresponds to. So then we get to reducers. So here's where the MapReduce sort of magic happens, where the framework provides you actual benefit. Reducers receive sorted intermediate output. So when the mappers run, they print out Firefox 1, Chrome 1, Firefox 1, Chrome 1, IE 1. And all this data, by the time it gets to the reducer, the framework has sorted all that data for you, and all the values for a given key are sent to a single reducer. This is fantastic, because this means a reducer is very low memory overhead. There isn't a memory constraint there, because it basically gets all the records for Chrome, and the only thing it needs to keep in memory is a counter, and it just keeps increasing it by 1 or whatever that value is. We'll see an example of this shortly. While mappers basically operate on each record, look at each line, print out Firefox 1, Chrome 1, reducers basically operate on each key, where now you're down to the reducer gets Firefox and then all the values, a huge list of 1s. But as it goes through those 1s, all it needs to do is just keep incrementing the counter. So reducers typically perform some sort of aggregate reduction on all the values for a given key. A single reducer will probably get more than 1 key, but because they're all sorted, it'll get all the values for a single key. Right? So you can think of reducers basically operating on a key rather than on a record. So if this is an introduction, we need to go through the hello world. And so the word count example is the hello world of Hadoop. You can go and Google and find probably much better examples than what I'm about to provide that show hello world word count examples using MapReduce across different technologies, using different tools. So depending on what you're interested in, you could probably go through that. Also, virtual machines are available from Hadoop distributors. You can go and download. We use Cloudera, so I'm familiar with the Cloudera VM. I know that others exist. And you can launch the VM, and it tends to have all the daemons, all the services already installed. So you don't need to bother with the Hadoop installation. You can also just fire up Amazon's offering, right? Because the Hadoop installation process is tricky. It's less tricky than it used to be. There's that Hadoop streaming, which we'll also get into in a minute. It's kind of nice. A bunch of these examples online for word count use streaming because they don't actually require a Hadoop installation. So you can basically walk through a mapper and reducer without having Hadoop installed. You can do it on your own machine. We'll see that shortly. We'll see that right now, because now is the demo. Okay, so this is Cloudera's VM, their, I guess, training VM. They actually offer 3, it seems like now. So I just grabbed this. This is the one with Impala in it. It's actually pretty nice. It used to be less nice. For example, you fire up the browser and they have a whole bunch of neat stuff already bookmarked for you, which is really cool. So you can visit the Hadoop daemons. There are examples installed. There are a bunch of gotchas. Like for whatever reason, Cloudera decided that MR2 should have been the default actions. So it might not work so out of the box for you, but let me go through an example. So this is a a mapper written in Python, chosen largely because it's a small number of lines and relatively easy to read. This is the word count example. This expects to receive input, just a block of text, and I actually downloaded something from Gutenberg onto its book. Right, so it iterates through all the lines of your document, or walks through, and for every line, we strip white space, right? And we split the line into words, right? Like default separator of space, right? So we now have this list of words, and for every word on this line, it spits out the word and the one. So similar to the browser thing, this is actually simplified because there's no parsing involved in the log record. All it's doing is it's splitting a line and printing out a word. So, for example, here, can you read that?
Can you please zoom in?
It's not sorted.
Well, it's not sorted, right, because this is just the mapper. But you'll see, so here I just print the line. So my mapper splits the line into words, and I could have echoed out a bunch of additional lines, and I'll show you that in a second. But the mapper basically prints out a word and then one, right? You could have more meaningful information if this were some sort of table that had real value. So the one is static, it's a hard-coded value, right? But you could, I don't know, your value could be something else, right? Some weighted value that you otherwise derive from the log record. In this directory, I have that book. So if I cat the book and run it through my mapper, a whole bunch of words and a whole bunch of ones. Now the information isn't sorted because the mapper doesn't actually sort the data. The MapReduce framework does that. So this is the magic of MapReduce. This is why running with MapReduce simplifies your work as a user or developer. You don't need to worry about the sorting. You don't need to worry about any of that. All you need to worry about is write a mapper that prints out this intermediate output, and then write a reducer that assumes your information is sorted, right? And that all the values for a key go to the same reducer. So this is your mapper, which we just went over, that's easy. Let me show you the reducer. This doesn't fit on one page, but the reducer gets our intermediate output, right? So it's Andy1, Hadoop1, Meetup1, right? And for every line, it, again, strips white space as practice, but then it splits the line into a word and a count. In our case, the count is always 1, right? It casts the count to an integer because by default, Python keeps it as a string. And it looks to see if the word that we've now received is the same word as the line it had previously seen. All right, so basically, the information is going to be sorted. So it's going to get Andy1, Andy1. And if you look at this code, all this bit basically does is say if it's a word, we're going to increment our counter by count, which is 1. And if it's a new word, I print out the now previous word and its value for count. And then I reset current count in word, right? So it gets Andy1. The first line does absolutely nothing. Next line, it gets another Andy1. So it says, well, the current word is equal to my word, so now my count is 1 plus 1 is 2. So now it knows Andy2. Next line comes, and now it's used Hadoop1. So it prints out Andy2, and then it starts counting for Hadoop, right? So this doesn't have to keep a map or an array in memory of all of the words, which is kind of the naive implementation, right? If you had to do this without the MapReduce framework, you might be tempted just to store it in like a map or an array. So you have your map Andy equals 1. You just keep incrementing that value. Then you just store the entire list array in memory. Yes?
Where's the sorting happening again?
So in the MapReduce framework, that's the agreement between mappers and reducers. From Hadoop's perspective, there's a shuffle and a sort, where all the different mappers basically move data around, and all values for a key are sent to a single reducer, probably from multiple mappers, and there's sorting that happens. But as a Hadoop developer, you usually don't have to worry about that. Now, everything is open, right? So simply put, you only really need to write a mapper and reducer. That said, at Pulse Point, for better or worse, we have our own implementation of a job manager, and we have custom sort implementations. So you can do all that, right? And there are basically secondary keys that you can use. So this is a simplification, but this is basically the allure of MapReduce. That you don't have to worry about that, right? That you can take it for granted. So let's go back here. If I print my line and it has two Andys, I run it through my mapper, and then I run it through my reducer. It's not interesting because Andy prints out twice, right? Which is to be expected. But if my reducer gets sorted data, now Andy gets out printed with a value of 2. And this is basically an emulation of MapReduce. So those hello world examples that will walk through streaming will do this. You'll see cat, mapper, sort, reducer. So you can pipe all the output through. And this way you can actually test your mapper and reducer scripts on the command line before you send it up to Hadoop, and then find out later that there's some problem with it. So this is a pretty rapid iteration to go through the Hadoop streaming if you're not like a real Java developer like me and more of a software engineer / hacker that hasn't been in Java too long. So that's streaming without Hadoop. Now that said, it's worthwhile to actually see how this works on Hadoop. So let me do that. This is Cloudera VM, so Hadoop is installed and everything. So I have that PG file, right? The book from Gutenberg. And I'm going to put that into HDFS. So you might just take it for granted, but I wanted to demonstrate I'm actually doing that. So I'm going to make a directory on a new file system called input. I'm going to upload that book to my input directory. Now I can do directory listing input. I see that my book is there. I can also cat that text file from the Hadoop file system just to prove that the information surely is in HDFS, right? And once it's there, I can run a Hadoop streaming job. And I cheated, and I put my streaming job in a shell script here. But let's walk through it. You run the Hadoop client command, and you run with the Hadoop streaming jar, which is part of your Hadoop installation. And here are a bunch of arguments. There are 4 real core required arguments. You have to have an input path and an output path. So I think those are straightforward, right? And then a mapper and a reducer, right? So this is the beauty of MapReduce. You only need to specify a mapper reducer, and the framework takes care of everything else. The file arguments here are because these are basically just local on my machine. The cluster doesn't know where they are. What I could have done was actually uploaded this to a shared location if the nodes in your cluster have some sort of shared file system. I could have given like a full path to them, and then I could have omitted these arguments. But this way, when I actually issue the command, my client will essentially upload those scripts to the cluster so that it can use them. So let's run this. So what did I do? I uploaded the book to that input directory. I ran that command, which specifies /input. So input and output are usually given as directories, but you can give full paths. You can actually have multiple input paths as well. The job ran quickly. I can jump over to the job tracker page, which maybe we can get into in Q&A, and see that there actually is a completed job. There are 2 because I must have run this before everyone showed up to prove that I could. And the stream job actually did run, and now I can go and I can do this. So this is the output directory that I specified, /output. You'll see that there's a logs file, or a location directory, but there's also that part file. So the reducers by default will write out these parts, because in a much larger job, you'll have many files instead of just one, and very many mappers that will usually write to a much smaller number of reducers. But each reducer will ultimately write out one or more files. And I can do something like this. So if I cat this is going to be kind of ugly, right? But this is the output, which is words and then frequency, my word count. It looks gross. Also, our definition of a word, you see, is kind of loose. It's anything that's between spaces, so you have all these word characters. But if I cat this and so this is, I'm just using the sort command, sorting it by the second column, numeric sort, reverse. So the most popular words show first, right? So this is, these are the 10 most popular words in that book, which is my output for my MapReduce job. And just to prove that I get the same result, the screen is cut off, but trust me, they are the same numbers. Right? So in I did that quickly, right? But I catted the file, ran it through my local mapper, sorted the output, pushed the output through the reducer, piped it through the same sort on the second column, numeric reverse, top 10, right? So in this example, there's no reason to use a cluster, it's a single file. But if I had a ton of data, I could have put all that data in HDFS, run that Hadoop streaming command, and gotten similar results. And that's MapReduce, right? Now this is streaming. You can actually write mappers or reducers in Java. You can use a whole bunch of different tools like Hive and Pig to create some abstraction there, to the point where you don't even really need to know what MapReduce is. Some of the products in the ecosystem don't even use MapReduce. They just exploit the Hadoop file system, HDFS. But that's my presentation. So I'd like to go into, oh wait, actually before Q&A, we are going to do the raffle, but also another plea for information and assistance. So things I'd like to walk away from eventually when I go home tonight is when should I do the next meetup? Like by default, I'm going to schedule something for next month, and unless something else pops up, I'm going to do the overview of the new projects or projects in the new ecosystem. I'm looking for anyone who wants to look for other topics. If anyone who has space to offer, speakers, I mean, you can read, right? Frequency meeting. Would anyone would be interested in meeting like every 2 weeks or something like that? The other idea was we could start doing some sort of hands-on exercises. Something like that, definitely need more assistance, right? So there's like equipment and space and just ideas. And more effort is required than I'm able to give. So help. So there's that. Before Q&A, let's just get the raffle out of the way.
All right. Yeah. We have these beautiful black and teal, very sleek water bottles, which are a limited edition run for us. So we're just going to do a raffle to give them away. All right, so the first winner is Vornado Realty Trust, Tendi Muchenji, Tendi. Tendi. Okay. All right. Okay, the second winner is Eric Werfel, Business Applications Manager. Okay. All right. This is for you.
Excellent.
Niant Dalal.
Thank you. Thank you so much.
Have Kala, like M. Yeah.